class for today is about, again, principles of energy and thermodynamics, but we will look more into, the laws of thermodynamics. Okay, previously kita tengok on a lot on the physics side, but today we will dive into some of the chemistry part. All right. So learning outcomes, what you guys should be able to do, okay, by the end of this lesson is to understand the law of thermodynamics in the context of energy, okay, and to describe entropy and energy change. Okay, so I'm sure that you guys already learned at some point or another about laws of thermodynamics, entropy, enthalpy, etc., etc. But what I can notice, right? You don't really, when we first learn about all that, we don't really connect that to the context that we are interested in. Okay, so this lesson is trying to, link what you already know, okay, with the energy context. Okay. So again, I keep on including all of these equations. So I hope this is hint enough, right? For text or for tests, for exams, all right? You can know that, these are something very important. Okay, so we have work energy principle. This one we learned last week. And then heat is the transfer of energy, of course. And then what is internal energy, aka thermal energy. And then, of course, the total energy is the sum of the energies. This one we touched upon last week as well. And lastly, the molecular kinetic energy. So these are all equations, okay? It may or may not be used later on, okay? But it's good if you can understand the principles of it, okay? So now, thermodynamics. Thermodynamics is actually, okay, it's the study of the general properties of energy, okay? It's very, if you look at that, it sounds very simple, okay, study of general properties of energy, but actually it encompasses a lot of things, right? So if you look at the figure here, okay, you can basically look at that in terms of principles, the processes, and also the properties. Okay, and the principles here is all the laws. You have the first law, you have the second law, right? And that is basically the basic of what is happening with the process, with certain processes. So to give you an example, okay, just a basic example for energy. Okay, this course is about energy, and the processes which is linked very well with energy is combustion process. Okay, you have your fuel, you combust that into carbon dioxide and water, right? So that is one type of process. I'm sure you guys, if you have taken chemistry before, okay, at any point, even in high school, or if you've taken in your first year, if you look at the chemical reaction, okay, like stage 12, O6 plus O2 becomes what? Okay, that is example of chemical processes. And then, of course, in thermodynamics, the substances, okay, if you look at just now about the combustion, the substance is the fuel, okay, the properties of that substance is also governed by thermodynamics. Okay, for example, is it in gas form? Is it in solid form, liquid form? So linking back to energy again, fuel, you have different types of fuel, right? So you have those in terms of gas, you have natural gas in gas. Okay, you have the petrol, the liquid LNG, okay, that is in form of liquid. And you also have solid in the form of coal, right? If you're looking at power plants. Okay, so that is giving a very brief introduction about thermodynamics, if you look at that in the context of energy and its application. Okay. Of course, if you study thermodynamics, you always see this like first law, second law, third law, right? So, however, there is also zeroth law. Okay, and it's funny because with zeroth law, it's actually something or a principle that comes after this first three laws has been established for hundreds of years. Okay, so zeroth law, that's why it actually describes something that is very, very basic, and it should come before the first three. Okay, and people back then, they were saying, okay, we should have this new law as the fourth law, but there are arguments against that because this new law basically is something that governs the first three. So it's the most basic thing, right? And eventually they gave the name zeroth law, so zero. So it comes before that, but actually it was discovered after the three. Okay, just giving a historical perspective. So what is zeroth law actually? Okay, zeroth law, it's, last week we talked about temperature, right? So temperature is the average kinetic energy of a substance, right? So zeroth law actually gives the formal definition of temperature. Okay, it might sound really, really, oh my God, takkanlah tak ada definition of temperature back then kan? So actually tak ada, there's none. So zeroth law ni, what it says is, if two systems are in thermal equilibrium with the third system, then they are in thermal equilibrium with each other, and there is no net exchange of thermal energy between them. Okay, so it's a mouthful. You might not understand it in the first glance, but basically, you can look at that with, you can relate that with thermometer. Okay, if you have a thermometer, this form, yeah, not the one where you go to shops and they, check your temperature using that one. So it's this one. This type of thermometer, okay, is actually the temperature when you put that under your tongue, okay, and you're saying, okay, the thermometer is measuring your temperature, your body temperature. Okay, so you can see that the system is different now. So your body is one system, okay, and this thermometer is another system, right? And inside that is the whatever form is in there. So before it used to be mercury, but now people are using alcohol because mercury is very dangerous. Okay, there's a lot of cases where this breaks, right? And then the mercury is dispersed, and that is very, very dangerous. Okay, guys. So if you have thermometers at home, please make sure that it's not mercury. If it is, then you have to change that to alcohol ones, okay, because that is much, much safer. Right. So going back, okay. So what is happening actually? Okay, the thermometer, the measurement, okay, it is measured through the expansion of this. Okay, remember? So if you really think about it, okay, you compare temperature with length, for example. Okay, you have something, you have a pen, for example. You can measure the length of this using ruler. Okay, so you have actually, okay, if you measure from here to here, then here is 0, and this is the value of the length. But with thermometer, with the temperature, it's really different actually. If you have no concept of, boiling water or ice, okay, really think about that. How do you measure zero temperature? Okay, of course now in our mind, we already link 0 degrees Celsius with ice, okay, the temperature where water freezes, and then 100 with boiling temperature. Okay, so we have that. That was the problem back then. Okay, they didn't have this concept, and they really need to point out why temperature is needed. Okay, so in this case, why this is very important is because thermometer, it doesn't really measure temperature. Okay, it's if you look at A and B, A is the body, B is the the thermometer. Okay, if A and B is in equilibrium, okay, so it's at the same temperature, right? I hope you can still follow me here. So if it's at the same temperature, there's no heat exchange, remember? Okay, so heat exchange is 0. So with using thermometer, with the expansion of C is this expansion, you can actually measure how much temperature that is. Okay, imagine if you do not have temperature, you do not have thermometer, it's going to be a hassle how you're going to measure any temperature. Okay, because there's no measurement of temperature other than something that you link with, okay, expansion, or the one if you go to the stores, the one that I mentioned before, where they test the forehead temperature, that is without contact, and that is using radiation, right? So that comes to my next point, which is calibration. Okay, so calibration is very important, especially now when we are looking at, with COVID. Okay, so I don't know if you guys had ever experienced this. So you go to a place and they take your temperature, and it's something like 32 or 30. Pernah tak? Did anyone of you ever pernah kan? So you have to remember, yes, 30 ada yang 20 something. That means, immediately means that the thermometer is not working. Okay, it's not possible for the temperature to be lower. So you can go up to 36.9 if I'm not mistaken. Okay, but if you get something like 35, that is definitely not your body temperature. Okay, there's a lot of, because if you use something like this, there's no body contact, okay, and the accuracy will be affected by the environmental condition, okay. You have the air temperature, so you might measure the air instead of your forehead, okay, or the wind speed. Maybe that place is very windy, so it disperses the heat somehow. So you have very low. So that's the point that I have now about, linking COVID with temperature. Okay, so do your part. If you see something like this, then tell the shopkeeper, okay, your thermometer is not working. This one is not, okay, it's not possible, right? So, okay, temperature scale. This is just a refresher. And I'm sure you guys can find it on your own, but I just put it in the notes so that it's easier next time if you want to do any of your exercises or studying for your exam, you have this with you already. Okay, so this is how you are changing, sorry, you are changing between Fahrenheit, Celsius, and Kelvin. Okay, but remember always in thermometer, in SI unit is Kelvin. So if you're doing any calculations, okay, with regards to that has temperature in there, usually it uses Kelvin. So be very careful about units, especially while you're doing calculation. Okay, so one more thing, zero temperature. Okay, you have to think about, remember just now we talked about there's no actually measurement for temperature. And the easiest way to imagine that is by imagining, is there a 0 point temperature? Okay, don't think about Celsius. Celsius 0 is water freezing, right? But this is in Kelvin. Okay, in nature, it's absolutely impossible for you to get negative 273.15 Kelvin. Okay, that is the absolute zero. Okay, coldest possible temperature, but it's not happening in nature. Okay, there's a reason for that, and we will look at that later on. Okay. Oh yeah, another thing is, yes, at absolute zero, theoretically, substance would have zero internal energy, which is another reason why it's not possible to have absolute zero. Okay, because remember, all molecules, it vibrates. Even at the coldest temperature, it has its own vibration. Okay. All right, next slide. First law of thermodynamics. Okay, so first law of this is actually a broad statement of the conservation of energy. You learned this already last week. Okay, so energy is conserved, and this is the equation that describes that. Okay, so the internal energy, the changes in internal energy of something, of your system, okay, is Q minus W. So Q is the heat and W is the work. Okay, so remember back when we talked about heat and work last 2 weeks, right? So by general definition, the first law says that the change, okay, the change in the internal energy of a closed system is equal to the energy added to the system by heating. So any heat that you give to the system minus the work done by the system on the surrounding. Okay, I know that it sounds really, you cannot imagine how, you can use this or how it relates to in real life, but we'll go into that afterwards, so don't worry. Okay, now, this is also very important. Okay, the signs, the convention of signs for, heat and work. Okay, so anything that is added, okay, if you add heat to your system, will be considered positive. Okay, or something is done to the system, the work is done to the system, it's positive. But if the heat leaves the system or the system itself does something, okay, and that will be designated as negative, right? So this is very, very basic, okay, but it can get really, really confusing once you get into calculating something, okay? So FYI, so that's why really, really iterating this right now, okay? But as long as you can understand what is what is considered positive and what is considered negative, then you'll be fine, right? So again, first law is this one, yes. Then the extension of the first law for a moving system. So just now, if it's stationary, but if it's moving, okay, remember in first week, we talk about kinetic and potential energy. So if there's any movement, then you're definitely going to have these two, right? So any changes in that will be equal as well to this, because we are conserving energy, okay? Conservation of energy. So at the same time, we can also relate work and ideal gas, okay? So this is how you can correlate W, work, with what is happening in a system of gas, okay? Negative P delta V, right? So this is called PV diagram. Okay, I'm not sure if you guys still remember, but in PV diagram, okay, you can calculate work. Okay, from whatever state that your molecules or your systems are at. Okay, so it might be quite abstract right now, but we'll try to link that to what is happening in real life, right? So please consider a system of an enclosed cylinder. Okay, for example, this one. So inside the cylinder is a gas, an ideal gas, and you have a movable piston. Okay. So in this situation, okay, the piston is, you can move up and down on its own, or if work is done. Okay. And the easiest way to think about that, if you look at here, the first law of thermodynamics just now, delta U equals to Q minus W. So Q is the heat, W is the work, right? So if, for example, this cylinder is in contact with a heat reservoir, okay, and a very large reservoir at that, so that any change in temperature in here, you know, it's not, it can be ignored, basically. Okay? So you will have a situation, okay, where it's either the heat moves in, yeah, from the reservoir into your cylinder because you know it's in contact, or you have a situation where you push down or you pull up the piston. Okay, so what's going to happen to the gas inside, right? So in one situation, the first situation, when heat flows into the system, okay, remember, so this is hot, this is cold, so it moves from here to here, okay? And what happens to gas when you heat it up? Anyone? I just want to know that you guys are still there. Okay, what happened to gas bila you heat it up? Ada ke jawapan kat sini?
Terkeluar ke doktor?
Imagine this is closed system. Huh? Sorry, tak dengar. Expand. Siapa tu? Najwa. Sharifah, no Najwa. Sorry lah, I terpaksa panggil nama penuh sebab tak nampak korang kan. Okay, betul. It's expanded. Okay. So bila dia expand, definitely the volume increases. Betul tak? So if you look back, yang equation before this, okay, W equals to P delta V kan. So you will have situation where volume increase, so work is actually negative. Okay, because work is done by the system. Okay, system tadi. So gas tadi yang bergerak, dia yang push the piston naik atas, because it's expanding. Okay, so it's moving, it's doing something, so it's doing work. Bila do work, remember tadi previous few slides, work is done by the system, that's considered negative. Okay, so another situation pula, if heat leaves the system, okay, gas tu akan start compressing, okay, they start compressing, and then work is positive because the volume is decreasing. Okay, volume is decreasing, work is positive. So if you calculate, if you look at it just like this, okay, you can understand the theory, okay, and later on, whatever form of questions you find, gonna be easy for you to figure out. Okay, science is very important, okay, because we have U equals to Q minus W. So if you mess up with the signs of Q and W, it's gonna be really, really, you know, it's really hard. So it's not something that is hard. So I think you guys will be able to do, you know, to understand and to implement this. All right. So now kita tengok PV diagram tadi. So because in PV diagram, so you have P and V. P is the vertical line, V is the horizontal line. Okay, from here actually you can calculate W, okay, of any system. Okay, so imagine this one just now. You have state 1 where it's a higher volume. Okay, so you can actually link that to PV diagram here. Okay, you have this one is the state 1 here. Okay, and state 2 is here. For example, okay, this might not be what's really happening, but you can look at the volume change. Okay, just from the volume change. So state 2 is definitely the one with the lower volume, so it's here. So you can actually calculate how much work is done or being done to the system by having the PV diagram. Okay, because sometimes, right, you can have something like this, like piston, okay, and you can actually visualize like what is D, what is actually the V, the volume, okay, and you can calculate W. But if you do not have anything like that, and you were only given PV diagram, okay, how are you going to do that? So this is the way to do it. You have to integrate the area underneath this. Okay. Now, example, simple example. Okay, if you add some volume of heat, some amount of heat to a system, and then the system does 3,000 joule of work. So the net change in internal energy, ikut je lah yang tadi, delta U equals to Q minus W, and then you have 5,000 minus 3,000 joule. Okay, pay attention to the signs, right? So this is positive, okay, which means that yes, the system has a positive change of energy. Okay. And compare that to this one. So you have a liquid, okay, previously a liquid, and you change that to a gas at constant pressure, okay, and the volume was this, and it compresses into this one. So how much work is done in the process? So like this, for example. So this is how you are going to calculate that, right? So notice that this is negative, which means that the system, okay, the system that is before is liquid and now is a gas, okay, it is doing the work, right? Okay, PV diagram. All right, so Yanni, I don't know if you guys still remember processes like this. So you have constant pressure or you have constant volume. Okay, but I will leave this for your revision. Okay, the next 3 slides, if I'm not mistaken. Okay, this is all about, you know, isobaric, isovolumetric, and isothermal situation. All right. This one I have to highlight because it basically summarize what is being talked about in the previous 3 slides. So you have different types of processes, okay, and what is actually the constant one, and what is the prediction you can make from that, right? Okay. So what happens to work done in internal energy as gas expands? And what happens when gas compresses? Actually, we look at this previously, right? And this is the way you can link your PV diagram to work, internal energy, okay, and also Q. So for example, with work, okay, remember just now we talked about work done, work being done, confusing, right? But I have put in this slide here so you can actually visualize. So if gas is compressed, okay, volume C decrease and work done is positive, right? So if gas expands, the volume must increase and work done is negative. And you look at the where it moves in PV diagram. Okay, so basically in PV diagram, it's always going to be something like initial state and final state. Okay, initial state could be anywhere. Of course, that is also the true when you're talking about final state. So let's say this is state 1. If it moves towards this area, okay, you can definitely just say, oh, volume decrease, work done is positive. So it's easy. So if you have a PV diagram, basically, and you just look at where the arrow is moving. Okay, if it's moving there, left side, okay, you can immediately say, or you can immediately understand in your mind, it's going to be W positive, and this is going to be W negative, right? And of course, in internal energy as well, okay, you can actually link internal energy and temperature actually, okay? So it's directly proportional. So if PV increases and T and U also increases. So again, if you look at your PV diagram, kan, for example lah, kalau dalam test or in exam, you are given PV diagram, okay? Immediately you can already say, okay, if it's moving here, then what's happening? T and U also increase. Okay, I hope you can understand why this all of this is very, very helpful when you are looking at PV diagrams. Okay, and of course Q can also be determined, the sign I mean, using this. So if you know already what is the sign of your delta U and the sign of W, you can definitely know what is Q, the sign for Q. Okay. So don't be too worried, janganlah risau. I'm not sure if you guys can still are following or not. I hope yes. Yeah. But anyway, we are moving into the second law of thermodynamics. Okay. So of course, in first law, we are talking about energy conservation. Okay. However, it doesn't tell us in which direction process will proceed spontaneously. Okay. So if you look at this type of situation, pernah jadi tak di dunia nyata? Something that is broken and then reassembles and then naik sendiri atas table. Ada tak? Any kind
Tak
of
pernah,
situation.
doktor.
Tak pernah kan? Sorry lah, tiba-tiba tanya soalan yang macam apa ni? Saya nak tengok semua masih ada tak tu? Senyap je semua.
Masih ada, doktor.
Okay kan? Alright, so spontaneously, okay, kalau just based on first law, this situation should be occurring. Okay, sebab there's no governing theory about spontaneity. Okay, so there's no direction, for example. Dan lagi satu, another example, pernah ke jadi you kemas your room kan? Pernah tak dikemas sendiri? Tak pernah kan? It's never spontaneous untuk kemas. Kenapa? Because you need to do some work. Okay. And that's why it's related to second law of thermodynamics. Okay, there's only certain processes or basically all processes. It can only run spontaneously in one direction or the other. It doesn't occur both ways. Okay, so we know in our minds what is happening spontaneously and what is not possible to happen spontaneously. So kita dah tahu dah, this one definitely tak berlaku di dunia nyata. Okay, and it's so easy for your room to get messy, rather than you are doing your spring cleaning, for example. Okay, you are ordering your room semua. Okay, we spend all that effort, all the energy, and then somehow continuously dia jadi macam ni. Okay, so why is this? So this is actually about entropy tau. If you have ever, if you still remember when back you learn chemistry or physics, you come across the concept of entropy. Okay, entropy is something that is moving from order to disorder. So something that is, you know, has its own order, it will spontaneously go into a state of disorder, because that's the way the universe goes. Okay, and that is governed by the second law of thermodynamics. So, of course, just now we talk about what can occur and what do not occur. Okay, the direction or the flow of that. Okay, so we link that again to heat. Okay, so you can definitely know heat can only flow spontaneously from a hot object to a cold object. Okay, it never the other way around. Okay, unless something is done to do that. Okay, so if you just put your hot water on your table, okay, after 5 or 10 minutes, the heat is going to disperse. Okay, but it's never happened that you put your cold water on your table and suddenly it freezes. And never happen on your table unless you put it in your refrigerator. That is another issue. That is another situation. Okay. So, like I mentioned before, entropy, order to disorder. Okay. So you can just think about that as natural processes, they tend to move towards a state of greater disorder. Okay. Another example, easy example, if you make coffee, you put in your milk, you put in your sugar, okay, and you mix it up. Okay, you got a uniform solution. Okay, you got your uniform coffee, sedap kan minum coffee, right? But if you do the same thing, it doesn't separate back into milk and sugar. Okay, that's why you can say that, you know, so if you look at milk and sugar as its ordered form, okay, it's never going to be the other way around, right? So thermal equilibrium as well is a similar process, okay, because the final state has more disorder than the separate temperatures in the initial state. Okay? So just to give you a perspective on that, if you look at state of matter, okay, from something that is solid to something that is a liquid. Okay, so at lower temperature, when the thing is solid, okay, it actually has a more ordered situation. Because if you look at the molecules is very uniform, you know, it's very closely linked to each other, okay? Whereas when you heat that up and it becomes a gas, remember the vibration that we talked about before? So vibration is increasing, okay? And it keeps on moving all over the place, all right? And when that happens, that is the disorder that, you know, is meant in this situation, okay? Because it's no longer in, you know, very packed, uniform kind of matter, but it's now in a form where it's slowly dispersing everywhere. Okay. So, apa kaitannya dengan energy sebenarnya? So if you look at heat engine, right, it's easy, of course, to produce thermal energy using work. Okay, but how does one produce work using thermal energy? Okay, macam mana sebenarnya turbine works? Okay, so a very good example of this kind of you know, energy transfer or energy change is shown in a heat engine. Okay, So heat engine is actually a device that changes thermal energy into mechanical work. Okay? And the mechanical energy can be obtained from thermal energy only when heat flows from high temperature to a lower temperature. Okay. So the analogy is like this. Okay, you have your situation where this is water wheel, by the way. So water wheel, tempat yang tinggi. Okay, air is from a higher elevation. Okay, so this is considered higher energy. Kenapa? Sebab it's elevated, so potential energy. Okay, I hope you can still remember that. Okay, elevation potential energy is high. Okay, so you can look at that as a state where the energy is the highest in this system. Okay, and as it goes from this high state energy to a lower energy, okay, it does some work. Okay, because you know, you look at the wheel as it rotates, it generates mechanical work, and that work can be used for, you know, back then when they don't have any electricity, this can be used to move something. Okay, and later on people use the same concept to, you know, in turbines, and they generate electricity from this type of work. You have this rotation, you have this mechanical work, you can transform that into electricity. Okay, so this is an analogy of heat engine. So imagine that this one is water. Okay, so you have your high potential energy, etc., etc. So in heat engine, okay, just now, very hot, very hot situation, okay, where it's a high temperature reservoir. Okay, and as the heat moves from this high temperature place to a lower temperature, okay, the temperature difference is gonna generate the work. Okay? So this is actually related to if you look back at few slides before at the piston stuff. Okay? That is how you can basically, you know, get useful work from the movement of pistons. Okay. So the high temperature reservoir transfers an amount of heat QH to the engine, where part of it is transformed into work, okay, and the remaining goes to the low temperature reservoir as QL, right? So it's very similar to this one before, okay, which is the in form of this, and you can look at that to heat engine in particular. Okay, so we will only discuss engines that run in a repeating cycle. Okay, so that when you say it's in a cycle, so the internal energy is actually zero, okay, because the system returns to its initial state. Okay, I'm not sure if you guys, if you want to look more into this, you can look into internal combustion engine. Okay, that's actually, if you drive your car, okay, that is the principles of which your car moves, for example. Okay, how the energy is transformed from the fuel that you put into your car into the movement of the wheels that propels the car forward or reverse, for example, right? So useful heat engine runs in a repeating cycle. Okay, so you get the internal energy, the changes is zero. So you can actually get or calculate like what is the W, okay, what is the amount of work produced by your engine from the temperature of the reservoir, for example. Okay, right. So this is another representation. Okay, and this is a steam engine, by the way. So you have this one is it's very similar to before as well. Okay, if you wanna look at that as the analogy, and you compare that to here, right? So the high temperature is where because this is steam engine, okay, so steam is definitely going to be generated. So you have the steam reservoir, which is a very high temperature, and this energy or this heat will move through the condenser, which is a lower energy reservoir. Okay, so the movement there will give out the work in the form of, you know, when you use the piston. Okay, so it's expanded and it's compressed, and that system is going to give you useful work, right? And of course, this one, if you want to look at internal combustion engine, okay, this is actually what happens in your car. Okay, so in your engine, your car, this is what is actually happening. So you have your spark plug here. Okay, so internal combustion engine always have spark plugs. So this is different if you have electric cars. Okay, electric cars is not going to use internal combustion engine because combustion, there's also the keyword there. It means something is being combusted. Okay, and that is your sorry, and that is your fuel. Okay, so your fuel and air mixture will come into here and it will be sparked off, and the energy generated from the ignition, okay, will drive your sorry, will drive the wheels of your car basically, right? Okay, so I will go very quickly on this one. So efficiency is very it's quite easy to calculate. The efficiency of heat engine is the ratio of work done to the heat input. Okay, so always remember efficiency is something that comes out over something that you put in. Okay, and it applies to everything basically. So if it's in heat engines, then it's something like this. If it's energy conversion efficiency, okay, we look at energy in over energy out. Sorry, energy out over energy in. Okay, so that's why I say if you are really, if you master the basic principles, then you are able to look at everything, you know, with a different eye, okay? And you can link everything actually. Okay. So Carnot engine. So Carnot engine is actually a theoretical engine. It's not an actual engine because in this sort of engine, it says that it has no friction, which is actually impossible, which is why it is an ideal type of engine. Okay, but in that engine, okay, you can actually calculate the efficiency of a heat engine, and it will consist of all the 4 types of processes that will, if you remember just now in PV diagram, when we are talking about, you know, how a state moves from one state to another, okay? And of course here, so PV diagram again. So this is the representative of that, what is happening at each situation. So A to B is isothermal expansion, B to C is adiabatic expansion, okay, C to D here is isothermal, and D to A is adiabatic compression, right? So this is something that can be calculated easily in an ideal situation using a Carnot engine. Okay. So efficiency of heat engine again. Okay, for an ideal reversible engine, you can use this basically to, if you have the temperature, okay, then you can actually calculate what is the efficiency of that particular engine, okay, which is really useful, okay, if you look at, okay, it's gonna be easier if you look at it like this. So let's say you are a structural engineer or a mechanical engineer, okay, and you are designing an engine, okay. So you can actually calculate the theoretical efficiency using this equation, right? And if you want to test that in real life, okay, you have a setup where you can measure the temperature, okay, the heat reservoir and the heat sink, okay, one which is at higher temperature, one at a lower one, okay, you can calculate the efficiency of that. So that is in engine, but because we are looking at energy systems, right? So not only engines, of course, in power plants as well, and also all types of machines that uses energy. So the energy efficiency can actually be calculated in such a way, right? But it depends on what is actually the use of such appliances, right? So don't worry too much. This is just a theoretical representation of engines. Okay, I know that maybe some of you might think, tak guna pun benda ni kan. So yes, at this point, I don't think you guys are specifically going to use Carnot engine, for example, but it's a useful thing to know. Okay, and I hope you can link that to other energy systems as well. Okay, so why 100% efficiency cannot be achieved? Because the core reservoir needs to be at absolute zero. And remember before, we already talked about how achieving absolute zero is impossible. Okay, so where does the energy go? Okay, of course, remember, was it last week that we talked about energy efficiency, and I told you about, bicycles. Okay, there's always going to be some losses due to friction. If friction is something in mechanical system, it's something that cannot be avoided. Okay, and it's always going to be there because you are using something. When you are transforming one form of energy to another, it always involves some mechanical systems. Okay, and mechanical system is always gonna include friction, and that's why you have frictional loss. Okay, always, all the time. So it's never gonna be a situation where you will have 100% efficiency in anything. All right. So entropy. So actually, the second law of thermodynamics, if you really look at the classical definition, there's a lot of different, I think there's 3 or 4 definitions, okay? But it mostly talks about entropy, okay? So just now, we talk about order to disorder. That is something that is entropy as well, because the concept of entropy is actually quite complicated. Okay, and the easiest way is to say something like that. So from a state of order to a state of disorder. Okay, and then you can also define the change in entropy actually. So you can actually calculate that. Okay, when you know what is Q, or the amount of heat added to the system, and you know the temperature, right? So notice that T is down here, okay? So if you want to have, if you want to relate that to what I said before about efficiency, okay, remember efficiency is never 100, okay? Why? Because there's always losses. And a situation that is possible where efficiency is 100 is a system where there is no entropy at all. Okay, so the change in entropy here is 0. And how that can be achieved is if T is at absolute zero. Okay, so this is the not to say graphical. So this is the equation in the equation form, what I had discussed with you previously. Okay, so if you have here 0, then you can have a situation where your efficiency will be 100. But because that is impossible, so it means that definitely there's always going to be a change in entropy in everything, every situation, right? And the total entropy of an isolated system never decreases. It always increases. Okay? So if you link that, it's now about heat engine then, but we also have something like refrigerator, air conditioner, and heat pumps. Okay, so basically it can be thought of as heat engines as well. Okay, but it's operating in reverse because you are extracting the heat from something. Okay, remember just now we talked about your water. If you want to freeze that, you put that in your freezer. Okay, so what's going to happen is actually the heat is extracted from your water, okay, into the cold reservoir. And then you exhaust the heat to the hot reservoir. Okay, so it can be refrigerator or it can be air conditioner. It works the same, very, very similar. Okay, so if you have a refrigerator here, okay, this is the graphical representation of the figure just now. Okay, so your refrigerator, if you ever look behind there, what is happening, okay, it always looks something like this. So you will have your compressor down here, and you will have your, so the temperature outside is your heat reservoir, okay? And the work is done by the compressor to, take out all the heat inside the refrigerator. Because remember, in natural kind of situation, heat always moves from high heat to low heat, okay? Which is why in refrigerator and air conditioner, you are using work or you are using power to drive this process, okay? So if you think about that and you think about your refrigerator or your air conditioner is a better example, okay? So why do people say if you want to reduce your electricity bill, you have to set the temperature at a higher level? Okay, so instead of pushing it to 16, okay, 16 degrees Celsius with your air cons, okay, you put that at around, I've heard one of the articles I've read recently says to put it at 24. Okay, so if you think about that, it makes sense because, the amount of work needed as you go colder is going to be even more higher. Okay, so if you have a smaller difference between the two, which is the outside and the inside temperature, okay, you will use less work and definitely you will use less electricity and your bill is less and you are happy. Okay, that is how you can, one way to look at that, right? Of course, again, performance, I just put this in because in case you want to do some calculation regarding your refrigerator performance, for example, yeah. And of course, lastly, heat pump. So we don't really use this because we are in a temperate country, okay? So, but in places where, has 4 seasons, in winter, it's very, very cold, okay? And again, this is something similar again. Okay, so heat pump can heat a house in winter, right? And the performance can be calculated as such. Okay, so you have your cold temperature outside and you want to keep warm inside, you have your heat pump. Okay, so you are actually keeping the energy inside. Okay, all right, so why actually delta T or temperature difference is needed to get work? So why does a heat engine need a temperature difference? Okay, this is not a question. I will just answer. Otherwise, the work done on the system in one part of the cycle will be equal to the work done by the system in another part, and the net work will be zero. Okay, so this is the long version or long explanation, but you can just look at it this way. If there's no temperature difference, okay, the system is in thermal equilibrium. Okay, so definitely you're not going to get any work done, right? So it's the analogy is something like your refrigerator, for example, is broken, right? And the temperature inside your fridge is similar to temperature outside. So there's no work done by your system, by your compressor. Okay, which is why there's always gonna need to be temperature difference in order to get W. All right, so that brings us to thermal pollution. Okay, so it actually, if you think about it, this is like a cycle actually. So as global warming increases, right, the temperature outside, the temperature outside is getting higher. So I know everyone noticed, it's getting hotter and hotter. Okay, and if you ask your parents, for example, what was the temperature like maybe 20 or 30 years ago? Not like this. Okay, it's getting hotter because global warming is happening, right? And as global warming happens, as you are getting hotter, you're going to use a lot more energy to bring that heat, to bring that temperature down, for example, in your house. Okay, so you're using air conditioner. Okay, an air conditioner, okay, if you look at that, you're gonna use more and more energy. And this will drive, the heat generation again, because you are actually producing more and more carbon dioxide, producing more greenhouse gases. Okay, and another thing as well. So if you look at current electricity generation, okay, you have something like this where even if it's using biomass, okay, so biomass is a renewable resources compared to fossil fuels, for example. Okay, and you look at solar power as well. Okay, in these two kind of situation, okay, you are using something. Okay, so in this case, in biomass, you are changing the chemical energy into electricity, and again for this one, you are transforming solar power into electricity, right? And remember, there's always going to be heat or temperature difference. And that is why you always see cooling towers, okay, when you look at power plants, any types of power plants. Because, for example, this one, for solar power. So the solar cells actually, it relays the temperature or the light into the collector here, okay? And the collector there will transform that light into heat, and heat will go into turbine as well. So it's using the same thing like when you're using biomass. So it's actually producing heat. In one way or another, it's producing heat, which will move your turbine, and turbine will generate the electricity. Okay? Because there's heat, that is why cooling towers are there. Okay? So the heat output of any heat engine, any types of heat engine, okay, is referred to as thermal pollution, and it must be absorbed by the environment. Okay, so even if you look at the cooling tower here, okay, they are actually dispersing the energy, okay, from the one that you collected, okay, using the layman term here. So whatever energy that you have from your energy resources is transformed into useful energy. And at the same time, remember there's always going to be energy loss. Okay. And when you are looking at large systems like power plants, okay, that energy loss is actually going to the environment. That is why it's called thermal pollution, because that heat has to be absorbed by the environment. Okay. So, of course, not only thermal pollution, we have air pollution emitted by power plants, industries, and consumers. And of course, most forms of combustion result in a buildup of CO2, and that contributes to global warming, right? So of course, this one can be, this kind of situation, it can be minimized through careful choices of fuels and processes. But for thermal pollution, it is a consequences of the second law of entropy. Okay? Remember, no efficiency is never 100%. So there's always going to be energy loss, and that is unavoidable. Okay, so it can only be reduced by reducing the amount of energy we use. Okay, so reflect on that a bit, right? So it's not going to be something impossible. For example, we are talking about global warming, climate change, okay, and the power industry, the energy that we are using every day is actually one of the major contributors to greenhouse gases. Okay, and that's why it relates directly to the CO2 that is in the atmosphere. Okay, so how much energy we are using is actually giving impacts to the environment. Okay, so we have to look at what types of that's why people are looking at increasing efficiencies of of systems, and then we are looking at alternative forms of energy. Okay, a lot of this comes from this particular idea that the energy we use is costly to the environment. Okay? And of course, if you look at the Earth as well, it's actually a heat engine. If you still remember geography, for example, okay, the Earth cores, okay, the heat exchange between the cores to there is actually what gives the geothermal energy, for example. It gives the alternative to other forms of energy which we can actually use, right? So linking that to global warming, okay, if you look here, so actually the places where the global warming effects can be felt, okay, is actually here. If you look at that, the dark red is the hottest part, okay, and that is why the people, and at the same time, this is also, where the people are focused on. So the population are majorly on this side of the earth rather than, at the Arctic or the Antarctic. Okay, so we have to think back at effects of, energy in terms of that. Okay, right. So at the same time, of course, if you look at heat engine as well, okay, it's a natural process. Okay, this is a natural process, and from this is where we got our climate, for example. Okay, so we have something like sea breeze and land breeze. Okay, so what is happening during the day, where if you remember, we talked about heat capacity last week. Okay, heat capacity of water is actually higher compared to warm land. Right. So what happens during the day? Okay, as these two are exposed to the sun, the land is going to be heated much faster, and it becomes warmer, right? And as it becomes warmer, you have this circulation, because remember, heat goes from hot to cool, okay? And you will have your wind system, okay? And that is the opposite that is happening at night time, okay? Because water at night has already started to get warm, okay? Because it takes longer time for it to get hot compared to the land, where it becomes colder much faster. So you have this type of situation where you also have the circulation, so from warm to cool. Okay? And when you look at that, that is just at the coastline, but this is actually what drives the monsoon. Okay, and if you look at the wind movement, the sea breeze, land breeze, this is actually the link between, how our world sustain itself. Okay, the climate is very closely related to the temperature difference, right? So if you have hotter land areas, land mass, okay, and it might mess up our climate system. Okay, and you see this nowadays with the storms, the natural disasters occurring because the climate is intricately linked with global warming. Okay, so I'm sure you guys know this already, so I just want to highlight that. Right, so far, any question? Habis. That was the last slide. That's why I was asking, like, if you have any question or anything.